Now that we've derived both Routh's and Henry's law, we could actually go back to the in-class problem, and we could actually solve for the mole fraction of CO2 in the liquid phase. In order to fully solve for it, we need to apply a couple of more of these eponymous equations from MEB1. And so one of the other equations that you learned about in MEB1 is Dalton's law, which just says that the total pressure in the vapor phase is equal to the summation of the partial pressures of each species. Okay? All right, and so that means that our total pressure is equal to the partial pressures of water and CO2. And from Routh's and Henry's law, we can relate those partial pressures to the liquid phase mole fractions. So we have our saturation pressure for water, and for CO2 we have the Henry's law constant. In order to get the saturation pressure for water, this is where we use Antoine's equation. So Psat, that's equal to 10 raised to the A minus B over T plus C. We have all those constants, and so at a temperature of 298.15, the saturation pressure for water is this. Okay? And so if we go back to our Dalton's law relationship, we could write the mole fraction water in the liquid phase in terms of the mole fraction of the CO2 plus X CO2 H CO2. We have one equation and one unknown, so we could solve for X CO2. P minus Psat H CO2 minus Psat W, and we find that the mole fraction of CO2 in the liquid phase is a little over 1%. All right? And so by using our chemical potential framework, we were able to derive two equations that we could use in order to solve for the mole fraction.